All right, Naomi will be presented and introduced by Mike Stamatikos.
Yes, hello everyone. It's my pleasure to have the opportunity to work with Naomi this summer. She comes to us from Columbia High School in New Jersey and will be attending Cornell in the fall. So that's a good school. Very proud of her for that. She also came with a lot of academic preparation and in particular very good research experience working with the Swift data set from the XRT instrument and in the context of Python code. So the projects we chose for her this summer kind of pivoted from that research experience and explored some more options. In particular, her project focuses on multi-messenger exploration of GRBs. We're in this incredible time in history where we can look at particular astrophysical events through different lenses, not only of light frequency, but also of things like neutrinos and gravity waves. So she primarily focused on looking at GRBs that were detected by the Burst Alert Telescope on the SWIFT mission and correlating the gamma ray emission with potentially reconstructed events in IceCube, in particular muon neutrino reconstructed events. And the goal there would be to see if there was a coincidence which could reveal microphysics of GRB that's unknown and also potentially give us another source of cosmic rays, which we've known for over a century. And the second part of her efforts were to look at calculating a spectral lag, which is the delay between the arrival times of photons in different energy bands. And this has been very useful in trying to estimate distance when redshift is not available to us. And the distance is critical for the energetics, and the energetics is critical for calculating how many neutrinos you might see or might not see. And then that would allow you to start constraining models in the case of an absent detection. Very proud of her work this summer and very happy to hear that she's interested in continuing these studies, but I will let her explain this to you in more detail. Thank you.
Naomi, do you want me to share your slides or do you want to share?
I've got it.
Cool.
Here we go. Is it visible?
Not yet. Sometimes it takes, oh, now it is.
Okay. Well, Dr. Sarti has kind of just summarized my whole project, but here it is. So, um, I've been working on a multi-messenger analysis of SwiftBat GRBs. And it's not loading. So what's a GRB? So gamma ray bursts are extragalactic bursts of typically high energy gamma rays, um, which is the highest energy and lowest wavelength form of electromagnetic radiation. These are associated with high energy events and are kind of split into two lengths, long and short, at the 2 second mark. So what we care out here, long gamma ray bursts, such as this one here, are theoretically associated with various stellar collapse events, such as black hole formation and supernova. So you look at the bottom right over here. This is what is called the fireball model of a GRB. This one specifically shows black hole formation, where a low energy gamma ray burst is released in the prompt emission as the star kind of explodes, and then and then shortly after there is an afterglow period with a high energy gamma ray burst as well as a variety of wavelengths of other wavelengths of electromagnetic radiation. So the primary instrument that my data is coming from is the Swift Observatory, which is a GRB observatory in the 15 to 300 keV range, so very soft gamma rays that you detects gamma rays via a array of semiconductors and then supposed to face it with its other instruments to get afterglow data in ultraviolet, optical, and X-ray. Now, neutrinos. So, for those who are already aware, neutrinos are nearly massless and neutrally charged leptons. They're which makes them very hard to detect. They're only detectable via the outcomes of their weak interaction. Um, there's three types of neutrino tied to the three flavors of charged lepton, electron, muon, and tau. But what we care about here, and because of what we care about here are muon neutrinos as uh, when a muon neutrino travels through the Earth, um, it and all the way through the Earth and reacts with something, releasing a muon. The path of that muon and the Cherenkov radiation it releases, traveling through the ice in a detector such as IceCube, can be tracked roughly back to the area of the sky where it came from, which cannot be done with electron and tau neutrinos. They just release a kind of explosive cascade. Now, so first part of my project is a neutrino and GeoB cross correlation, specifically both a temporal and spatial cross match using Python code and detections from 2011 to 2023. So I want to clarify that the GRBs, this is not all the GRBs Swift has detected in that period, but more only the more high value ones, those without a lot of noise or anything. And if you look on the right, I have a little diagram of what theoretically should be released from any high energy source, such as an AGN or supernova. So you have the gamma rays, which are photons, which means although they're high energy, they can lose energy in path or be fully absorbed, and therefore you lose information. Cosmic rays, which don't exactly follow a straight path because, well, they're protons, they're attracted by every single magnetic field in the way. So it's hard to figure out where they actually came from. And neutrinos, which don't interact with pretty much anything, so they go straight through. So if we can actually associate them with something, we can find a lot of information from them. Problem is actually detecting them. Now, the second part of my the second part of my project is GRB spectral lag calculation. Now, spectral lag is the time difference between detections of a GRB in different energy bands. In this case, I'm using Swift batch channel 1 and channel 3, which are 15 to 25 and 50 to 100 kV. Now, this is less a new research and more a modernization of earlier research on the topic, as a lot of that research was done with now rather outdated technology and methods, including the use of a no longer used coding language called IDL. So a big part of what I'm doing is converting everything that was used for that into the modern standard of Python. So as kind of my proof of concept for this, I'm using a rather astrophysically important GRB 080319b as my proof of for as my proof of concept and kind of case study. So before I get into the results, what is the point of all this? So on the neutrino side, now, as I already said, neutrinos can provide a lot more insight into Jury events that we can't get from photons. But more importantly, if we associate neutrinos with a specific gamma ray burst, well then we now know that the photomeson reaction that you see here, where a proton and a gamma ray cause this whole cascade of reactions that eventually results in some neutrinos. Um, well, we know that that happened, which means that we know there are protons there, which gives us evidence for the theory that cosmic rays, which we don't really understand where they come from right now, is it's kind of and can accelerate protons way faster than CERN or any other Earth-based particle accelerator. Well, basically, that supports a theory that cosmic rays are accelerated by GRBs and the high energy events that produce them. Now, on the spectral lag side, spectral lag can be used to calculate, so as Dr. Zanatigos kind of already explained, spectral lag, when you have a bunch of GRBs with known redshift and you calculate the spectral lag, you can use that to create a model, an algorithm that can then calculate the redshift of GRBs without known redshift based off of their spectral lag, which you can use to get distance, which is needed for energetics calculations because, well, you can't figure out what the energy is if you don't know how far it traveled. Um, which is not only needed for studying the mechanics of the jury, but can also help you predict how many neutrinos should be emitted by that event. However, since it's not really feasible for me to do all of this on my own with the limited time that I have, big part of what I'm doing is updating old techniques that I said, and also creating kind of a tool set and a foundation for other people to doing this research to work off of without having to go through a lot of old research and try and replicate it from scratch. So methodology for the neutrino side of my project, well, it's basically a bunch of Python code that you can see here. On the spatial side, I used an overlap of the error radii of both Swift and IceCube. However, because of IceCube's massive several degree error radiuses, rather than arc minutes or arc seconds, as you'd usually expect from most apparatus, kind of just created a whole bunch of meaningless matches. However, on the temporal side, I only used the GRB's T90 duration, that is the duration of 90% variation, which only brought one temporally coincident pair. However, they were not spatially coincident. So um, no big results. However, this analysis, of course, must be continuously repeated as any new data on either side comes out. So it's hardly complete. Now, on the spectral lag side, my project was based off of replicating this case study on GRB 080319B, see in the bottom left. So what I did was I coded out functions for the modified cross-correlation function that you can see here. This is the code, all in Python, and then create oopsies create code to fit that both across several potential lags with 32 millisecond binning, and then fit that to a modified Gaussian distribution with with the error bars determined by 1,000 times Monte Carlo simulation and with 95% confidence. Now, here's kind of the current state of that. So it does definitely fit into the so the fit lag is where the peak of the fitted curve is. So, and it definitely does fit into the 29 plus or minus 4 milliseconds result that you would expect from the paper that's based off of. However, as you can see from the curve and the error bars, it definitely needs quite a bit of fine tuning and is currently not really ready for other people to use um, or to be kind of used for any sort of publishable science. This is the equation that it's fitted to, by the way. Um, so kind of the conclusions here. So of course, there's no big surprises in the GRBs and neutrinos. So since IceCube has so much error and inaccuracy, I kind of just need more evidence to make any real conclusions. We can't take the lack of evidence as a conclusion within itself. However, one thing you can do to expand this is bringing CAM3 net data to provide full coverage since IceCube only covers half the sky. On spectral lag side, it's very much still an ongoing project that I'm currently working on. As you've seen, the code is only partly functional and needs a lot of fine tuning and cleaning up. Once the proof of concept is done with GRB 080319B, I intend to expand it to GRBs that haven't had these kind of calculations done on them before to fully make sure it works. And then so other people can make a use of my work here. I either turn into either a GitHub repository or a Python module that other people can just download and use my code without having to figure out how to write it all themselves. And I also like to thank Dr. Stanatikos for kind of teaching me about all the astrophysics I needed to do this because I'm decent at coding, but I did not know nearly half of what I explained today when I started this. So thank you. Questions?
It's a lot of work. Are you gonna try to keep working on this? Or
Um,
I think you're gonna be going to college, so you may be able
I
to.
am, and I also have other research on tournaments that I'm still trying to finish my paper for. But yes, I do intend to continue researching this if I can.
Okay, well, good luck.
I
Definitely.
just want I just want to say very impressed with Naomi's grasp of the astrophysics. There's a lot of moving parts here, and hopefully we can continue. But it was very much a pleasure to work with her and happy about the progress.
Excellent. Amazing, amazing presentations from everybody.